Okay, so right off the bat, every single electronic system has to start somewhere. And that somewhere is by interacting with the world. It all kicks off with what are called inputs. You can think of them as the system's eyes and ears. Basically, it senses. And the name for these inputs? Sensors. It's their one and only job to notice something happening in the real world. Maybe the light is fading or the room's getting a bit chilly. They take that information, and this is the crucial part. They translate it into an electrical signal. It's like they're converting it into a language the circuit can finally understand. And here we've got two perfect examples. First, the light-dependent resistor, or LDR for short. Super simple. The brighter the light that hits it, the less it resists electricity. And then you've got the thermistor. Same idea, but for temperature. The hotter or colder it gets, the more its resistance changes. See? It's a really basic but clever way for a circuit to measure what's going on. And this isn't some abstract theory. You see this stuff every day. You know that street light that just knows when to turn on at night? That's an LDR at work, sensing it's gotten dark. Or how about your refrigerator, always staying at the perfect temperature? That's a thermistor inside, telling the cooling system when to turn on and off. They're just simple sensors, but they're doing these really important jobs all around us. Okay, so the system has sent something. Now what? Well, that information has to go somewhere, right? This brings us to part two, the process. This is basically the brain of the operation. It's the part that takes the signal from the sensor and actually makes a decision. And at its most basic, the decision maker is just a switch. I mean, it doesn't get simpler than that. It's a yes or no choice, on or off. You flick it, the circuit connects, and electricity flows. You flick it back, the circuit breaks. That's control in its purest form. But what if you want the circuit to make that decision all by itself, without you having to flick a switch? Well, that's where this little guy comes in, the transistor. The book has a great analogy for this. Just think of it as a tiny digital gatekeeper for electricity. It just sits there, waiting for the right password before it lets anything through. So how does our little gatekeeper work? It's got three little legs, or connections. The one we really care about right now is called the base. So when a tiny little electrical signal, we're talking just about 0.6 volts, shows up at the base, that's the magic password. That tiny signal opens the gate, and whoosh, a much bigger current can flow through the other two connections. It's basically an automatic switch, but with zero moving parts. Pretty cool, right? All right, quick recap. We've sensed the world. We've made a decision. So now we have to actually do something about it. This is the final piece of the puzzle, everyone. The output. This is where all that electrical signal stuff gets turned back into a real-world action. So an output device is basically the polar opposite of a sensor. Remember how the sensor turned light or heat into electricity? Well, the output takes that electricity, the stuff the transistor just gave the green light to, and turns it back into something real, like light or sound. It closes the loop. Input, process, now output. And our textbook gives us two perfect everyday examples. You've got LEDs, light-emitting diodes. These things are everywhere. They're super efficient at making light. They're in your phone, your TV, modern light bulbs. Then there are buzzers. You know, the sound that wakes you up in the morning from your alarm clock, or the beep your car makes. In both cases, they're just taking an electrical signal and turning it into something useful for us. So for a really simple circuit, that three-step dance, input, process, output, is all you need. But what if you want to do something more complicated? Well, then the brain needs a more specific to-do list. And that's where programming enters the picture. It's literally how we talk to the circuit and give it instructions. And for these more advanced systems, we use something called a microcontroller. Don't let the name scare you. It's just a tiny, tiny computer on a single chip. So instead of just one transistor making one simple yes or no decision, this thing can follow a whole list of instructions. It's a way more powerful and flexible brain for our system. And what's really cool, and what the textbook makes clear, is that you don't have to be some kind of coding wizard to do this. A lot of the time, you can program these things using simple flowcharts. You just use different shapes for different commands, like an oval means start or end, a diamond is for making a yes or no decision, a rectangle is for an action, like wait for a second. It's visual programming. Let's just quickly walk through the example from the book. So first, you start the program. Then you hit a diamond, which asks a question, hey, is the switch on pin 3 being pressed? If the answer is no, it just loops, asking again and again. But as soon as you press it, the answer is yes, so it follows that path. Turn on the light, wait for 1 second, then turn the light off. And then it goes right back to the beginning to check that switch again. Just with those few simple shapes, you've created a pulsing light. It's awesome.
By breaking it all down into these little building blocks, the book shows us that underneath all the scary complexity, the core logic of electronics is, well, it's actually pretty simple. It follows this really clear, predictable pattern.
And this is that pattern. This is the big takeaway from our whole deep dive today. 1. Input. You sense the world. 2. Process. You make a decision. And 3. Output. You take action. That's it. A sensor notices something, a component like a transistor decides what to do, and an output like an LED or a buzzer does it. Seriously, everything from the simplest little gadget to a crazy advanced robot is built on this exact same 3-step logic. And the cool thing is, now that you know this pattern, I promise you, you're going to start seeing it everywhere. In your microwave, in your car, your thermostat. It's all there. So the next time any device around you beeps or lights up or just does something on its own, try to break it down. Ask yourself, okay, what was the input, what was the decision-making process, and what was the final output? So my question to you is, what's the first simple electronic system you're going to spot?